Hi there, I'm Lena, I'm a PhD in mathematics, and this is my blog about mathematics around us. And today I would like to talk about multidimensional space. How can we imagine a multidimensional space, and how many dimensions do we live in? Let's go.
Liftoff of the Delta rocket carrying GLAST, a gamma ray.
Heinlein has a story, the house that Till built. The architect Till built a house in the form of a sweep of a four-dimensional cube. He argued this decision by the fact that this house will occupy the area like an ordinary cube, but there will be a lot of space in it because it consists of 8 rooms, of 8 cubes. However, just before the project was handed over, the earthquake occurred, and the sweep collapsed into a four-dimensional cube. In our space, it began to look as an ordinary three-dimensional cube, but inside it, different miracles began to happen. For example, a person moving from room to room eventually turned out in the room where he started to grow. And from the windows, the amazing, unexpected views opened. Cool idea, and why not always build like that? In general, we often hear that in fact we live in a multidimensional space, but only 3 of it are available to us. And there are some entities that pass by us in the 4th dimension. Let's try to imagine a multidimensional space and also try to figure out how many dimensions we actually live in. If we move away from the idea that the dimension may be only spatial, then it is quick obvious that we live at least in a 4-dimensional space, because we can use the time as a 4th dimension. But there is no way to reduce our 4-dimensional space to 4 spatial dimensions, because time and length, or latitude or height, are not compared with each other. That is, our 4-dimensionality does not equate us with a 4-dimensional Yeti. However, what of the world we live in contains more dimensions? How to find out? To this, let's do a thought experiment. Suppose we have an ant that is crawling along a strip of paper and intends to crawl to point A, which is located immediately behind the farthest edge of the strip for it. In this case, he is a 2-dimensional entity. If we close this strip, after all, we are in 3-dimensional space and can do this. Then nothing will change for him in the world that he can observe. In addition, he will never crawl to point A, located in his 2-dimensional world. Moreover, it will always be possible to draw a straight line between his position and point A, and in those cases, when the strip along which the crawls does not obscure his 2-dimensional view, he will see that it is moving away from him and not approaching. When the strip obscures the view, he will not see point A at all until he arrives at his starting point from which he started his journey. And if, on the contrary, imagine that he has an obstacle in his way, as a wall, for example, we could bend a strip of paper so that it passes over this obstruction. The ant would again not notice anything, and for a 2-dimensional observer on the strip, the ant would pass through the wall, and look, passing through it would look distorted, because this observer would see only its 2-dimensional projections. If you and I lived in a reality in which there are 4 spatial dimensions, then we would from time to time find ourselves in similar situations, and someone would pass through the worlds. But if without ufology and other mysticism, then there are not documented such phenomena. True, there are serious doubts in the case of a voting machine. Perhaps it has some kind of portal to the fourth dimension for paradox, then maybe our time is a two-dimensional. This, of course, is not so cool that being a four-dimensional Yeti, but at least it would be possible to move from one point to another instantly for an observer from our usual time. Let's see what effects we could observe in this case. If time is two-dimensional, then we can represent it as a plane with two axes. Both are temporary, t1 and t2. And for simplicity, let's turn out entire observable spatial world into one axis, let it point up, and we call it x, y, z. What if the time t1, which we observe and measure on the clock, is fixed, but the time t2 changes? After all, this means that a certain spatial object can be simultaneously in different states, and this is nothing else than we are trying to imagine when it comes small particles and quantum effects. That is, when we try to imagine a quantum superposition, we act as a five-dimensional entities for whom time is two-dimensional. And do you know there is another phenomenon called quantum entanglement? Between quantum entangled particles, the interaction occurs instantly, at exactly the same time, even if they are very far from each other. Maybe time is spent, but just along the t2 axis, which we do not observe. Or maybe these particles in four-dimensional space are one particle, and we perceive them in three-dimensional space as something divided. Next, we have 2 points marked on our usual time axis, t1, A and B, and we move from A to B. But the coordinate along the t2 axis behaves like a logarithmic curve that is infinitely receding along the t2 axis. It infinitely approaches point B, but in no way and never will approach it. This effect is theoretically assumed when the so-called event horizon is reached. A black hole is a star of such a mass that light, due to its huge gravity, cannot overcome its attraction. And the event horizon is the state of the observer. It should theoretically occur if this observer falls into a black hole. Any object approaching the horizon from the observer's perspective appears to slow down and never completely cross the horizon. That is, it turns out that in some special states that we can only imagine and observe their manifestations, time theoretically can behave as two-dimensional or high-dimensional, and there can be more spatial dimensions. Now let's try to imagine a multidimensional object. How can this be done? Let's do the same as we imagine a three-dimensional object, and we can only see them drawn on a plane. What allows us to understand that we have a cube in front of us, and not a square of a rhomb with a strip in the middle. We must see the object from different sides, that is, its different projections, and see how it moves. Then we can imagine this object. Let's try it with a four-dimensional cube. Its face is an ordinary three-dimensional cube. Obviously, the projections of all faces are the same, so we will draw one. Let's proceed by analogy with how we will draw a two-dimensional projection of a three-dimensional cube. In general, at first, we would draw like this. But if we remember that the back face of the cube is farther from us, which means it is smaller for us, then it will be so. A four-dimensional cube has a face a three-dimensional cube. By analogy, this will look like this. Now, let's see how it moves. Look, it turns out that some edges pass through each other, and some square faces seem to be distorted, although we know that each of them is nothing more than an ordinary square. Let's remember our ant, which passed through the wall. These distortions are connected precisely with the fact that we perceive projections on a three-dimensional space. So, if suddenly you ever have to draw special effects for a film about a four-dimensional Yeti, remember this effect. We will perceive it as something that is constantly geometrically distorted. Thanks to watching to the end. Like, subscribe to the channel, and write in the comments what topics it will be interesting to discuss more.